Hey, welcome everybody. I'm Paola Cappellara. I'm a professor in nuclear science engineering and in physics here at MIT. And today is my great pleasure to introduce Guoqing Wang, who is a student in my quantum engineering group, and the rest, or some part of the group, is here in UV party. We are all looking forward to hear from Guoqing, who has been working these past few years in developing and really pushing the performance of quantum devices based on spins in diamond. So we will hear from him how we can use these quantum systems to develop very powerful quantum sensors, such as magnetic field sensors, and how we can use them also to simulate very interesting quantum dynamics, and in particular studying symmetry properties of the systems. So before starting the seminar, I just want to remind you a few things. So first of all, please wait to ask a question until the end of the talk. And you can ask question, you can start asking the question in the chat. You can write them up at any time, but we will read them after the talk. And also at the end of the talk, you can just raise your hand and we will be able to call upon you. Okay, so I'm really looking forward to hear from Guoqing on how we can develop better quantum sensor simulator using solid state spins.
Okay, thanks Paula for the nice introduction. It's a great honor today for me to share some of my recent research update about developing better quantum sensors and simulators with spins in solid state platforms at a quantum engineering group at MIT led by Professor Paola Cappellara. So in recent years, quantum technology has brought us a lot of useful applications. And the basic principle of the quantum technology starts from the so-called Schrödinger's cat. In the classical world, the cat can be either alive or dead, while in the quantum world, the cat can be both alive and dead simultaneously. So the smallest unit that can preserve such a property is called a quantum bit or qubit. And the basic principle for such a property is called superposition principle. So making use of the superposition principle, people have developed many different quantum applications, including quantum computation, which could potentially achieve exponentially faster computing power than classical counterparts. In quantum sensing, people have used a single spin qubit to actually sense magnetic field at nanoscale with high sensitivity. And in quantum simulations, people have used different platforms to simulate and engineer and characterize the novel matters which are usually hard to study in condensed matter and materials science. In this talk, I will focus on introducing our recent progress on sensing and simulation using solid-state spin defects. So the quantum device we use is a spin defect in diamond called nitrogen vacancy center, which consists of a substitution of nitrogen adjacent to a vacancy center. Such an NV center is sensitive to magnetic field like a magnetic needle. It has two energy states which are separated by 2.87 gigahertz frequency, and such a two-level system is used as a qubit in our following applications. So the basic principle of our quantum sensing and simulation application is based on this so-called Rabi oscillation. When we apply an external magnetic field, which has a frequency on resonance with your two-level system frequency, such a field will drive oscillation of your quantum state, which can be measured as here. So this oscillation is called Rabi oscillation. From the oscillation frequency, we can extract what's the amplitude of the signal field. And this is the basic principle of quantum sensing we will introduce in the following projects. And the same Rabi oscillation protocol is also used for control the qubit state. When you apply such an external field, you can let the qubit evolve to any arbitrary state you want it. So based on various quantum sensing protocols, people have developed many different sensing applications, including the sensing of magnetic field, which was pioneered by these two works in 2008. And by making use of the coupling between the NV center with the crystal lattice, including the phonons in the crystal, people have also developed strain sensors and thermometers using NV centers. And this year, a colleague in our group it's also proposed that we can even use NV center to sense coronavirus. And in simulation, actually, because in diamond, there is a rich spin bus consisting of various different spin defects in the bus, we can use of those many-body interaction to explore some interesting phenomena such as spin transport. And in these different applications, people have achieved the performance of nanoscale spatial resolution and high sensitivity up to picotesla for magnetic field sensing. So what's the remaining challenges we want to overcome? And what kind of better quantum sensors we want to build in our projects? So one main challenge for current sensors is that it is typically hard to simultaneously optimize several different performances. For example, if we want to sense a vector magnetic field, usually we want to use different orientations of NV center in the lattice. And then because we use different spin defects in the diamond, actually we lose the spatial resolution at nanoscale. And another performance, which is the sensitivity, is actually depend on the number of qubit, which is this number n, and also the coherence time of the qubit you can achieve. So to achieve better sensitivity, we can simply increase the total number of qubits, but this usually introduces more decoherence, which means shorter T2 time. And it also makes it more difficult to control such a system. So there is always a conflict between the ensemble enhancement and the decoherence. And another type of challenge is some performance haven't been achieved yet. For example, the current sensors are still limited to frequency that is the NV resonance frequency, which is around 2 to 4 gigahertz or below 20 megahertz. So in the following, I will show that in series of our work, we actually provide solutions to all of these challenges. So let's start looking at this vector AC magnetometry. To sense vector AC field at nanoscale, we want to use single NV center. And to use a single NV center to extract different component of the vector field, we introduce a different reference frame, which we call it rotating frame. So now in the lab frame, we have a signal field along some random direction that we want to measure, and we can apply a resonant driving along the x direction to the spin sensor. And then in the rotating frame, which has a rotation about the z-axis with a qubit frequency, we can see that the longitudinal component still has the same frequency omega s as the lab frame frequency, because such a rotation commute with this z direction. And the transverse component has a different frequency because the rotating frame rotation is about z, so you have a frequency shift to the transverse component, which gives this omega 0 minus omega s. And the good thing now is that you have a tunable energy gap, which is along this x direction. So now, instead of doing the Rabi oscillation in the lab frame, we can do the Rabi oscillation in the rotating frame. What we need to do is we can tune this energy gap, capital omega, to match either the frequency omega s or the frequency omega 0 minus omega s. So we can let the longitudinal component or transverse component drive Rabi oscillation in the rotating frame. Using this method, we can achieve the sensing of vector components using a single spin. So to demonstrate this, we use a bulk diamond, and we use different locations of single NV centers to sense the magnetic field that is generated by this straight copper wire. And here we show the experimental result, where this blue arrows show the experimental measurement, which is quite consistent with the classical model. You may have noticed that actually for this method, we still need to tune this energy gap to match the frequency of the signal field. So that actually, because the energy gap capital omega is given by the amplitude of your micro driving, so you are limited by your micro power. So in this method, we are still limited to some frequency range, which is given by your hardware limitations. So how do we achieve the sensing of a broader frequency field? And how do we achieve the sensing of arbitrary frequency field. Now let's look at our second project which overcomes this challenge. So we propose a so-called quantum mixer to actually convert any unmeasurable frequency fields to measurable ones. Remember that to sense the signal field, you have to make the signal to be on resonance with the NV center to drive Rabi oscillation. And now instead, if you have a signal which is far off resonance with the NV center, we can apply another AC bias field with frequency omega b, such that the frequency difference of the omega b, omega s match the NV center frequency. So when this omega t actually match the NV center frequency, actually this effective signal can drive the Rabi oscillation of the NV center. So through this method, we can achieve the conversion of any arbitrary frequency field to match this NV center frequency, so we can achieve the sensing of arbitrary frequency signals. And the benefits of such a method is that we really don't need a real mixer, and we are directly using the quantum sensor itself as the mixer. So actually, this quantum mixer can be combined with any existing quantum sensing protocols, such as vector AC magnetometry, to build vector AC magnetometry for arbitrary frequency fields. So still, we are using the rotating frame to sense different components of the effective field, but now instead of tuning this energy gap capital omega, we can tune the frequency omega b to match these two frequencies with this capital omega. So we are no longer limited by the energy gap capital omega, which is limited by the hardware limitations. So now let's have a bit more detail about the theoretical background about this quantum mixer. Such a quantum mixer is based on so-called quantum frequency conversion, which we derive using the so-called Floquet theory. So let's use an example of a signal field along z direction with frequency omega s and a bias field along transverse direction with frequency omega b. And the basic idea of the Floquet theory is that you can convert the time-dependent Hamiltonian in the Hilbert space to time-independent one in the Floquet space. And then by solving the Floquet space Hamiltonian by performing some like block diagonalization, you can then obtain some effective Hamiltonian. And finally, after converting back to the Hilbert space, you obtain the real effective Hamiltonian in the Hilbert space. So the key result of this theoretical derivation is that when you have two frequency components in your Hamiltonian, their joint effect up to second order is given by their commutator with a frequency sum, omega 1 plus omega 2 here. And such a principle can be represented in this plot here. So we see that because we have a two frequency driving, we have two dimensions defined as the Floquet mode 1 and Floquet mode 2. And there are two different types of effect of this Floquet quantum frequency mixing. So one effect is so-called AC Stark shift, which consisting of two hopping process, which doesn't change the spin state. Hopping up, hopping down, the spin is still preserved. So such a term, which actually gives you this frequency shift or energy shift delta z. And this is the same as the AC Stark shift derived using any other methods. And interesting thing is that we have another term which gives rise to this spin flip, which is consisting of a hopping up here, but hopping down mediated by the other dimension of the Floquet space. So such a process will give rise to the spin flip, which gives you the sigma x, sigma y term here. So finally, in the effective Hamiltonian, you will have a shifted qubit frequency omega 0 plus delta z, and you will also have an effective Rabi driving with amplitude capital omega t, which is linearly dependent on the signal amplitude. So by measuring the effective Rabi oscillation, we can, from the Rabi frequency, we can extract what's the amplitude of the signal field, and then we can sense the amplitude of any arbitrary frequency fields. So now let's look at a bit more on the experiments. So as I have mentioned, we can still use the rotating frame to sense the vector component of the arbitrary frequency fields. So now, instead of tuning this capital omega to different resonance conditions, we can tune this frequency omega b to be omega s plus capital omega or omega s plus omega 0 plus capital omega to sense transverse and longitudinal component of the vector field. And the experimental sequence is that you apply a laser to initialize the spin to 0 state, and then we apply a pi/2 pulse to initialize it to +x state. And then we switch on this continuous driving, and the Rabi oscillation due to the frequency converted field will be observed in the rotating frame by applying another pi/2 pulse finally to perform the projective measurement along this +x. In the experiment, we also show that such a protocol can not only be combined with the continuous protocol, but also with the pulsed version, which is called CPMG, and this is usually more used in sensing AC magnetic fields. So here we use an example to show our experiment. So we use a 2.2 gigahertz NV center to sense a 150 megahertz vector magnetic signal. We see that the transverse component resonance condition appears around this 150 megahertz frequencies, while the longitudinal component resonance appears around 2.35 gigahertz, which is consistent with our theoretical prediction. And by parking at those resonance conditions and look at time evolutions, we see these coherent time oscillations, Rabi oscillations, from which we can extract the amplitude of the signal. So above, I have introduced our progress on sensing arbitrary frequency field. And now let's turn to the second conflict, which is the conflict between ensemble enhancement of the sensitivity and the decoherence. So actually, the decoherence in the ensemble is actually given by the energy variations, which is usually due to like inhomogeneity in your sample or temporal variations of your measurements. So for our system, we have an electronic spin one, which is the NV center's spin, and we also have a nitrogen-14 nuclear spin. Because both of them are spin one defect, so they have quadrupolar terms proportional to SD squared and ID squared here. And in addition, you also have a hyperfine interaction between the electronic spin and the nuclear spin. So corresponding to different electronic spin levels, ms equal to 0 and ±1, the nuclear spin will have different splittings between 0 and ±1. And if you look at the variations of the nuclear spin energy levels, actually we see that actually, for example, for this ms equal to 0, the nuclear spin energy between 0 and +1 is Q plus gamma and B. Typically, for nuclear spin, its coupling to magnetic field is very small because of a small gyromagnetic ratio gamma n. So usually this contribution due to the magnetic field coupling is small, while the contribution from its intrinsic interaction, including this quadrupolar term and also this hyperfine term for this ms equal to ±1 is more important. So if we look at the decay rate, we can see that for ms equal to 0, the decay rate of the nuclear spin is due to delta Q, while for ms equal to ±1, you have an additional hyperfine variations, which introduce more decays. So our solution to such a noise variation is so-called unbalanced echo. So the basic idea is that we can use the hyperfine interaction to refocus the quadrupolar interaction. So again, let's look at this evolution of the nuclear spin qubit. So the nuclear spin qubit undergoes a free evolution after an initial pi/2 pulse. So it's a free evolution in the transverse plane. And this is the typical Lamarck precession. And in the first period, we actually have the noise accumulation, which is due to this delta Q. So what we do is that we apply a spin flip pi pulse to the electronic spin to flip the electronic spin state to another state. So in the second part of the evolution, we have an additional hyperfine evolution AZZ term and also its variation delta AZZ here. So the total noise accumulation in this whole process is actually given by the sum of these two periods, which give you this T delta Q minus tau delta AZZ. So actually, when tau over T is equal to the ratio between Q and AZZ variations, we will see that the two interactions will refocus with each other, and then the noise accumulation term will be 0. So you will have the longest coherence time, hopefully. So this is actually demonstrated in our experiment. So when we sweep this pulse location and look at what's the coherence property of your qubit, we see that the optimal coherence can be achieved when the pulse location is at 0.18. And then when fixing at this optimal pulse location and look at the time evolution, we achieve a factor of 20 enhancement of the coherence time in comparison to the unprotected cases. So actually, such a coherence time reaching 3.3 milliseconds is already reaching the single qubit limit. So through this method, we actually solve this conflict between the larger number of qubits and shorter coherence time. Okay, so above all of the introduction about the quantum sensors, and now let's switch gear to turn to the introduction to the quantum simulators that we built. So what's the motivation here? So the basic motivation is that typically different symmetries will introduce different topological phases. However, in quantum materials and condensed matter physics, it is usually hard to grow some material with some desired symmetry. So people in AMO physics and other quantum platforms have used optical lattices and superconducting qubits to actually simulate a lot of different interesting topological phases and symmetries. And one interesting idea that we want to study is actually the correspondence between the Floquet theory and Bloch theory. The idea there is to use the time or frequency dimension to simulate the spatial dimension. As I have introduced in the quantum frequency mixing part, even though you have a single qubit, you can still apply several frequency drive to create such a two-dimensional lattice structure, and you can introduce some hoppings and transitions in those Floquet levels. So what's the challenges in this field and that we want to overcome to simulate more symmetries? So the first challenge is that usually to observe the complete energy transitions, energy bands in this kind of structures, we need to sweep a large parameter space, which usually requires strong driving. And this is still limited by the hardware, for example, the microwave power. And second, in different platforms, people have developed different protocols to characterize these different symmetries. Well, there is still lacking a general protocol, which is general to most quantum platforms, such as projective measurement, which can be used in any quantum platforms, no matter it's superconducting qubits or NV center or at the even atomic systems. So in the following introduction, we will show that we provide solutions to both of these two challenges. So to achieve the strong driving, we propose that we can engineer the phase modulated driving in the lab frame. So instead of applying a single tone sinusoidal oscillation, now we introduce this complicated phase modulation. Even though this waveform looks very complicated in the rotating frame, it can be simplified to a typical driven two-level system with a qubit energy defined along x direction with amplitude capital omega, and also the driving, which is defined along z direction with amplitude epsilon m. Because now this driving is defined by your phase modulation, so you are no longer limited by your hardware power limitation, so we can reach a strong driving, which means that this epsilon m can be made very large in comparison to this capital omega. So because here in the rotating frame, we have a periodically driven system, which is so-called Floquet system. And we also have this Floquet states. So we can observe the transitions between different Floquet states. To observe transitions between different Floquet states, we need to introduce some probe operator V, and we can define some transition element V mu nu, where this mu nu is denoting the Floquet eigenenergies, while this n denoting the manifold difference between these Floquet states. And what we can do is that we can perform the projective measurement onto each eigenstate of this probe operator, and then calculated this weighted sum. And we have theoretically demonstrated that such a PT, which can be measured by this projective measurement, is exactly equal to the expectation value of the probe operator. because now we have the time dependence of this V, we can perform Fourier decomposition to this V component, and we can see that different Fourier component amplitude will represent this transition element, and different frequencies will be the transition frequencies of those Floquet states. And here, this C mu, C nu are actually the coefficient defined by the initial condition. So through this method, we can actually characterize both the amplitude and the frequencies of the Floquet transitions between different Floquet states. And let's have a look at one example in a two-level system. Assume you have a probe operator V equal to sigma Z, so its eigenstate is 0 and 1. So actually, such a measurement is the typical Rabi oscillation measurement. And by measuring the Rabi oscillation and performing Fourier transformation, we see that in the Fourier spectra, we see the Floquet transition center bands and side bands under different initial conditions, which is set by this initial coefficient C mu, C nu. So from the amplitude, we can see the transition, we can observe the transition amplitude, and from the frequency, that's the transition frequency between different Floquet states. So now we know how do we engineer strong driving and how do we characterize transitions in Floquet levels, and how do we do to actually characterize dynamical symmetries. So for symmetries, any kind of symmetries, it can be defined by some symmetry operator. So in our case, we use the S to define such a symmetry. So such a symmetry is defined as a transformation up to our Hamiltonian. When operating this symmetry operator to our Hamiltonian, it will transform the Hamiltonian to a different time up to some constant coefficient. For example, for the Hamiltonian we introduced in the previous slide, sigma x represents a twofold rotational symmetry, while sigma z represents a particle Hall symmetry because it can map a positive energy state to a negative energy state. When the Hamiltonian has such a symmetry, the Floquet eigenstates will also have the same symmetry, and combining with how does the symmetry operator transform the probe operator V, we can have a series of vanishing conditions for this transition element V mu nu. So if we look at the experiment by observing, measuring the Fourier spectra as a function of this modulation strength epsilon m, we can see that all of this vanishing intensity is corresponding to the dashed line, which is theoretically predicted by the symmetry prediction. So we call this vanishing condition the symmetry protected selection rules, or symmetry protected dark state. In addition, we also have symmetry protected dark band, which is the vanishing condition for the susceptibility, which is a function of this SPDS. And we can also have more interesting phenomena, which is called symmetry-induced transparency, which is actually the interference between different Floquet transitions. And this can only happen when two transitions match the energy or become degenerate, which is shown by this experiment here. We see that when these two bands match here, we have this symmetry-induced transparency, which is also called coherent destruction of tunnel. So in this project, we show that by engineering modulated drive, we can engineer a strong driving, and by performing projective measurement, we can characterize the transitions in Floquet states, and we can use this in our two-level system to simulate parity, rotation, and particle Hall symmetries. So finally, let's have a summary and outlook of our next step. So currently, we have already achieved the sensing of vector AC magnetic field by using the rotating frame, and to solve the conflict between the vector magnetometry and nanoscale spatial resolution. And to solve the conflict between ensemble enhancement and the coherence time, we actually use the unbalanced echo to protect the nuclear spin, which achieves the similar performance as a single qubit. And we also developed so-called quantum frequency mixer to achieve the sensing of arbitrary frequency fields. And in the simulation part, we engineer and characterize dynamical symmetries by engineering those Floquet energy levels. So we have already achieved so many different applications of the quantum sensors and simulations. So what's the next step? So what haven't been done, or what we still want to explore? So actually, all of our applications that we have demonstrated here is based on the spin degrees of freedom in the diamond spin defect. However, in the diamond spin defect, we also have the charge degree of freedom, which is actually important, but is less studied than the spin degree of freedom. On the one hand, the charge degree of freedom will influence the stability and the sensitivity of your quantum sensor. On the other hand, once such a degree of freedom can be used as some tunable knob, we can achieve more benefits, such as high fidelity readout of the spin state, or even more tunable simulators with some tunable interactions in your sim systems. So recently, we built a wide field imaging setup to actually further extend the capabilities of our quantum sensors and simulators by studying this charge degree of freedom by looking at the temporal and spatial information of their dynamics. So the first step is to try to understand the interplay between the charge and spin, and then try to control such a interplay to actually develop even more applications and better performance sensors and simulators. Okay, with that, I want to end here, and I want to thank a lot to my advisor, Professor Paola Capellaro, and all of this work is in close collaboration with Daniel in MIT Lincoln Lab and Professor Julie in MIT NSC and MSc department. And all of this is in collaboration with also a lot of students and postdocs in the group and the department. Yeah. With that, I want to end here, and I'm happy to take any questions.
Thank you, Guoqing. Very nice talk. Okay, we are now open for questions. I said you can just raise your hand or write in the Q&A. So maybe I will just start so that people have more time to think about. So you introduced to us this nuclear spin protected ensemble of protected nuclear spins. What would the nuclear spin be good for sensing? What application do you have in mind?
Yes. So for the nuclear spin, so actually I have introduced that we have both electronic spin and nuclear spin in this NV center. So usually electronic spin is more used in some typical sensing applications, and nuclear spin is less used. However, for the if you want to sense the so electronic spin is more used for sensing magnetic field because it has larger gyromagnetic ratio, which has larger coupling. However, for the nuclear spin, it usually has a longer coherence time because it has smaller coupling to the external magnetic field, which means also smaller coupling to the noise field. So by making use of the longer coherence time, we can sense the rotation, which is used to build the gyroscope. And so that's the main application of the nuclear spin in quantum sensing. But making use of the long coherence time of the nuclear spin, we can also develop it as some quantum memory, like some memorize some quantum state and store some quantum information, which is important for its applications in quantum communications and quantum networks.
Thank you. So there is a question in the Q&A from Shibi Chen, who's asking, what is the microwave power you're using in the measurement?
Yeah, the microwave power, if you in terms of electronics, like some tens of watts, and in terms of the driving amplitude or the driving amplitude, which is the coupling between the microwave and the spin, which is on the order of 10 megahertz.
Okay, thank you. So there was a raised hand by Juan. Go ahead.
Yes, hi. This is Juan Sommer from Texas Instruments. So. Thank you very much for the interesting presentation. The first question is related to what is the expected sensitivity that you expect to achieve by using this method, in particular, the first part of your talk.
You mean the coherence protection part?
Yeah, when you use the mixer there or that experimental technique to actually, because at the end of the day, you're trying to measure magnetic fields here, correct? I mean, and your system can be used only to measure AC or also DC magnetic fields.
Yeah, so actually for these two applications, it's mainly developed for AC application, AC field sensing. Well,
and what will be your sensitivity for that and the limits for your the frequency range of applicability of this?
Yeah, so I would say that for this vector AC magnetometry, if you don't use the frequency mixing protocol, it will be the same as the typical sensor. It has no frequency sensitivity difference than typical sensor. So
I understand that using the Rabi oscillation, because one of the problems with the NV centers that we see is that they are not really sensitive, correctly? I mean, that's our evaluation that we have from the, and people have been mentioning the idea of using Rabi oscillation to enhance or increase the sensitivity of the NV center magnetometers, correct? So now you are bringing the Rabi oscillation here. So my expectation was that by using the Rabi oscillation, you could increase the sensitivity of the NV center so far.
Yes, actually, typically you have very different types of sensing protocols like RAMC, CPMG, Rabi oscillation. So usually Rabi oscillation is yes, as you said, it's better because usually the Rabi oscillation has longer coherence time than like the RAMC experiment or other experiments. Mm-hmm. So I believe the sensitivity improvement is probably coming from there. Yeah. So because here in our method, we also always use Rabi protocol. So we also have the benefits of the coherence improvement and sensitivity improvement.
Mm-hmm. But let's say you're expecting to get picotesla per root hertz, for example, sensitivity?
Yeah, so currently the picotesla sensitivity is only achieved with ensembles of NV centers. For a single NV center, it hasn't achieved the picotesla level sensitivity. So, but for hopefully, so because our protocol is no different in sensitivity with other protocol up to those coherence time difference. So actually, if we use this protocol using an ensemble of NV center, we could also achieve the picotesla sensitivity. But using ensemble, you also lose the spatial resolution. So that's always the trade-off there. Yeah.
Okay, I understand. Yeah. Yeah. And the last question here, I'm a little familiar with the free induction magnetometers that you use, I mean, some of the aspects of your presentations reminds me to actually that. In fact, on the free induction magnetometers using atomic vapors or cesium or rubidium and this type of cells, you actually measure the frequency of oscillation to get the magnetic field.
Yes.
And people have been achieving picotesla per root hertz of sensitivity there. Okay, so in your case, it seems that you measure amplitude, not so much frequency of the oscillation. Is that right?
So, yeah, so actually, I believe that in your free induction decay measurement of the magnetic field, you are measuring like the RAMC oscillation frequency. Mm-hmm. So in that frequency, for example, in this measurement, if you have some free evolution, which is some like rotation about z-axis, and then finally in this measurement, you will also see that evolution. So that is actually a frequency from your measurement in your RAMC oscillation. Well, actually, in different frames or in different definition, it also corresponds to the amplitude of the signal field. So actually, the signal field amplitude corresponding to the oscillation frequency in your signal. So it's actually consistent or the same thing.
Okay, I understand. Okay, thank you very much.
Yeah, sure.
Thank you. There is another question from Mani Chandra.
Hi, yeah, I'm Mani from Rensselaer Polytechnic. This incredible stuff. Is this all based on quantum superposition or is there quantum entanglement involved somewhere?
Actually, we are based on quantum superposition. So you see that here we have a power over 2 pulse, which actually create a superposition state between 0 and 1. Right. But actually in our projects here we introduced, we don't use entanglement because we always use the single qubit to do the sensing. But yeah, we could like using, there are a lot of different works that use entanglement to actually further enhance the sensitivity of quantum sensors. Yeah.
I see. So by measuring the decay of the entanglement in some way, or yeah.
So the entanglement enhancement is basically if you have like here we have one spin which is entangled, which has no entanglement, but if you have two spin which is entangled, finally your phase accumulation will be twice the one spin phase accumulation. So you have an enhancement. If we look at the sensitivity formula here, if you have n spin entanglement, you will have n enhancement of your sensitivity instead of square root of n. So yeah, that comes from there. Yeah.
If I may, I have another question. So you have a mixer, right? So you have
Yes.
have to have some underlying nonlinearity for it to multiply those two frequencies, right? So I didn't understand, what is that nonlinearity? What is that term in your Hamiltonian that's giving rise to that nonlinearity?
Yeah, that's a very good point. So actually, we do have some nonlinearity, but in some different definitions. So our nonlinearity actually is the second order perturbation effect in this Floquet energy levels. So actually, the final term is given by this two frequency hopping instead of a single first order process. So here, this is the nonlinearity. Yeah.
Thank you. Yeah.
Okay, other questions? Oh, here another question. Slide 16. I wonder, how do you derive the coherence time and decay? Derive the coherence time and decay rate. This is from Zhiyao Hu.
Yes, you mean, yes, how do you drive the coherence time and decay rate? So derive, I believe you mean derive.
How you derived it, yes.
Oh, yes. So yeah, so this basic principle can be understood like you can assume you have a large number of qubits, a large number of spins in some ensemble of in an ensemble sample, and in different locations you have different energy splitting. So finally, your total signal will be actually the sum over all of these different frequencies oscillations in your signal. And finally, if you have a range of different frequencies and sum them up, you will see the decay of the signal. And so this is the basic principle that why the decay rate of your coherence is related to the variation of your energy splittings.
So I guess there is a follow-up question from Shibi Chen. Does it mean that you're doing the sensing and frequency mixing with the same physical structure?
Yes, exactly. So because here, as I mentioned, we don't need a real mixer to do things. So actually the NV center itself is the frequency mixer, and it is still the quantum sensor. So we do everything using just a single NV center. Yeah.
Okay, another question, what are the challenges in fabricating a reliable NV center with entanglement for computing application? This is from Umit Sami.
Yeah, this is a very nice question. So fabricating NV center is not difficult. However, fabricating NV center with entanglement is typically hard because the NV center interact with each other through this magnetic dipolar interaction, and you have to bring them super close to have significant interaction to actually create some entanglement. However, even though you can try to make them as close as possible, which means you need to have a lot of nitrogen defects in your sample. However, when you have so many samples, it also becomes very complicated to actually control such a system. For example, how do you generate such an entanglement state, which is useful for quantum sensing? And it is still an open question in the quantum sensing community.
Okay. I think that we have another question from Mani Chandra. Go ahead.
Thank you. Yeah, just wondering, how compact is your setup? What does it look like? Is it like a chip, or is it like a whole tabletop situation?
So actually, for our setup, so this is so actually this center, in the center of this picture is our diamond. So this all of the other lasers and magnetic fields are generated by this optical paths and its magnets, and we apply the microwaves through this PCB board. So it is a very compact setup. So we want to note that actually our setup in the group is not optimized for practical applications. If you really want to develop some commercial application, you can always make it very compact and tiny. Yeah.
All right, thanks.
Okay. Thank you, everybody, for all the questions, and thank you, Guoqing, for a very nice presentation. Before we conclude, I just want to remind you that there's going to be another talks in this nano series. This will be on Tuesday, December 13th. And the talk will be by Peter Satterweiter from the EECS, Electrical Engineering Computer Science Department here at MIT. Okay, I think that that's all for today, and thank you all for coming.